In this lecture, we're going to look at a new element in the development of mathematics. We're going to see how art has really influenced geometry and all of mathematics within the past few centuries. I've been standing in front of a picture of the Lion Court at Alhambra in Granada because it's an excellent example of symmetry in art. There is all kinds of symmetry throughout Alhambra, and symmetry is really fundamental to much of what artists do. To be symmetric means to be left unchanged under some kind of a transformation. And as we look at the Lion Court at Alhambra, we see that if we do a mirror reflection of the building, this is a kind of transformation, shifting the left for right in a mirror image. Under this transformation, the picture is left unchanged. Quite intentionally, of course. It was built so that it would have that symmetry. The lion basin at the center also has a symmetry, a different kind of symmetry. It does have this mirror symmetry, so that if you look at the reflection of that basin, you get back exactly the same basin. But if you were to look down on the basin from above, you would see that it is surrounded by 12 lions, equally spaced, around the circumference of the basin. And so this means that if I take this configuration, the circular basin, with its 12 lions, and I rotate it by 30 degrees, I'm not going to change the configuration that I've got. And so we say that this basin has 12-fold rotational symmetry. I can rotate it 12 times by 30 degrees each time, and each time I rotate it, I get back to exactly the figure that I had before. There's another kind of transformational symmetry that occurs in Alhambra and that is present throughout the palace, and that is translational symmetry. The idea that you've got a pattern and that pattern repeats as you move horizontally, or it repeats as you move vertically. Such a pattern is often referred to as a wallpaper pattern. And the first of the illustrations of the kinds of tiling patterns that are at Alhambra is shown in this particular picture that shows this translational symmetry. And the thing about a pattern that has translational symmetry is that you can tile a surface of arbitrarily large size. The pattern is going to continue off forever in all directions, which has a fundamental religious truth hidden within it for the Islamic creators of this particular piece of art, the idea of the infinitude of creation. But it also is very appealing to create a pattern that has this kind of translational symmetry. Now, this particular pattern at Alhambra has more than translational symmetry. It also has rotational symmetry. We've got figures here where if we rotate them by 120 degrees, we get back exactly the same figures. Now, there are colors within this tiling pattern that disrupt some of the symmetry, and I think there was an intentional effort on the part of the artist to have the symmetry and yet have something that seems to break it. But if we just look at the geometric patterns, we see that not only do we have translational symmetry, we also have a threefold rotational symmetry. There is another type of translational symmetry or wallpaper symmetry that is shown in the next picture that shows a six-fold rotational symmetry. Now, if I take this pattern, which is going to repeat arbitrarily in both horizontal and vertical directions, and I rotate it by only 60 degrees instead of 120 degrees, I'm going to get back to exactly the same wallpaper pattern that I had before. Here is yet another example of a wallpaper pattern that is present in Alhambra. This particular pattern has fourfold symmetry, so I can rotate it by 90 degrees and get back to the original pattern. It almost has mirror symmetry, But if you'll notice, some of those bands that outline the figure actually overlap in ways that it doesn't quite have perfect mirror symmetry. And there's something very interesting going on here. You've got translational symmetry. You have, at first glance, mirror symmetry, and yet the artist has been quite clever in breaking that mirror symmetry. So it's not really quite there. It invites the observer to look at the pattern more closely and think about what's going on. Another example of a wallpaper pattern is given in Alcazar, the castle in Seville. This is actually taken from a metal door in the castle, and it shows another wallpaper pattern that has both fourfold rotational and mirror symmetries, but they're quite different from the other fourfold or mirror symmetry that we saw in the previous picture, in that in this particular case, the rotational symmetry has its center in the center of those circles, whereas the mirror symmetry is located at a different point. The mirror symmetry is located at the center of these lozenges. So one can have a wallpaper pattern that has both fourfold rotational and mirror symmetry, either with the centers of both of these symmetries at the same point, or you can have a pattern that has these symmetries at different points. So we've been looking at different kinds of symmetries, different kinds of transformations that leave a picture unchanged. We've looked at the mirror symmetries, we've looked at rotational symmetries, we've looked at translational symmetries, we've looked at various combinations of these. Another important kind of symmetry is what is called a dilation. And we see this quite clearly in the kinds of images that are often used where you have a picture, and inside that picture there is a smaller picture which is an exact copy of the large picture. And inside that small copy of the large picture there is an even smaller copy of the large picture, and this continues off to infinity. We call this dilation symmetry because if I take that small picture that's inside the large picture and I expand it out to the size of the original large picture, I get back the original large picture. So this is a transformation, this idea of dilating that small picture, expanding it out, or a dilation can be a contraction. So the dilation is either expansion or contraction, and to have a pattern that is left unchanged once I accomplish that particular expansion or contraction. The graphic artist Marius Escher, born in 1898, died in 1972, traveled to Alhambra in 1922. He was quite taken by the art of Alhambra, and he returned there in 1936 and began to do an extensive study of the kinds of symmetry patterns that he saw in the Alhambra, in the tiling of the walls, and the various kinds of transformations that were used. And he became fascinated by this idea of patterns that are left unchanged under various kinds of transformations. And he actually went back to the Netherlands, where he was from, after spending several months at Alhambra in 1936. He went back and he began to explore the mathematics behind it. There was a very important paper on these wallpaper patterns that was published by George Polya, one of the great Hungarian mathematicians of the 20th century, a paper that Polya had published in 1924, looking at all of the different ways you can take a wallpaper pattern and combine it with other kinds of symmetries, rotational symmetries, mirror symmetries, and so on. And one of the things that Polya shows in this paper is that there are exactly 17 different types of wallpaper patterns. If you've got a pattern that's going to repeat indefinitely in the horizontal and vertical direction, what kind of rotational symmetries can it have? What kind of mirror symmetries can it have? In fact, there are 17 of them. That result was not original to Polya. It had first been done in 1885 by Fedorov, and there are interesting questions that raises. What if instead of a translational pattern in 2 dimensions, you think of a crystal pattern, a translational pattern in 3 dimensions, which is going to be unchanged as you translate horizontally or vertically, or translate in the 3rd dimension of depth? How many ways can you combine such an invariance with various rotational and mirror symmetries? It turns out that in 3 dimensions there are lots of ways of doing it. There are 320 different ways of combining 3-dimensional translation invariance together with other symmetries. Escher began to create drawings, graphic art that used all of the wallpaper patterns, and fairly quickly he began to move beyond that and look at other transformations that mathematicians had been studying, and looking for creating art that was unchanged under these particular transformations. And one of the most important groups of transformations that mathematicians would use, it's a group that would come into importance in the 19th century, and as you will see, would actually come to play a role in the ultimate proof of Fermat's last theorem. This is a group of transformations that are known as the modular transformations. And they're one of the reasons why I talked about complex numbers and the complex plane so much in the last lecture, because understanding the plane as being made up of complex numbers is critical to understanding these modular transformations. So there are 2 basic modular transformations. The first of these is to take the object and translate it by 1 unit to the right or to the left. So one of the things about any of these transformations that they're studying is that they can always be reversed, and you can always then build on them. So if I can take my picture and move everything 1 unit to the right and it doesn't change, then if I move it another unit to the right, it again won't change. And so we get a translational symmetry, but only in the horizontal direction, not a vertical translational symmetry. The second symmetry that comes to play a role in the modular transformations is a kind of inversion. What you do is to take a point in the complex plane, let's denote it by the letter Z, and that gets translated into the point which is the negative of the reciprocal of Z. To understand what happens if I take a point in the plane, I want to think of this point in the plane as being represented by an exponential with a complex exponent. And in the last lecture, I explained how this can be done. If I've got a point in the plane, I need to figure out how far that point is from the origin. If it's e squared away from the origin, then that's going to be that distance, and that will go into my representation of this number. That will be the real part of the exponent, the number 2. And then if the angle of elevation is pi over 4 radians, or in other words 45 degrees, that goes into the complex part of the exponent. And so this complex number that is e squared away from the origin and at an elevation of 45 degrees, or pi over 4, is represented by e to the 2 plus pi over 4 times I. Now I want to take the reciprocal of that number. If I take the reciprocal of that number, that means taking the negative of the exponent. So instead of looking at e to the 2 plus pi over 4i, I'm going to look at e to the minus 2 minus pi over 4i. Now, the distance from the origin has changed from e squared to e to the minus 2. And when I take the reciprocal of any complex number, what's going to happen is that the distance from the origin turns into the reciprocal of that distance from the origin. If I've got a complex number that is 5 units from the origin, its reciprocal will be 1/5 of a unit from the origin. Something different is happening with the angle, though. The angle had been pi over 4 radians, an arc of pi over 4. That turns into minus pi over 4. So instead of traveling in a positive direction from the positive real axis, in other words, instead of traveling counterclockwise, we travel pi over 4 radians in a clockwise direction. Instead of moving above the real axis, we now move below the real axis. And so to take the reciprocal of a number is, first of all, to replace its distance by the reciprocal of that distance, and then to reflect that number over the real axis. So take the reflection across the real axis. Now, in the case of a modular transformation, we're taking z and replacing it not with 1 over z, but the negative of 1 over z. So there's one more action that has to take place. We take the distance, replace it by the reciprocal of the distance. We take that remaining point and reflect it over the real axis. And now we take the negative of that number. And to take the negative of a complex number, you simply draw the line from that number through the origin and go out the opposite side of the origin exactly the same distance. Now, one of the things that this does, if I start with a complex number that is in what we call the upper half plane, so I start with a complex number where the imaginary part is positive, it lies above the real axis, and I take the negative reciprocal of that number, that's going to change the distance from the origin. It's going to flip that number across the real axis, so I'm now below the real axis. And then when I take the negative, I wind up back above the real axis. So this transformation is one that takes a number that is above the real axis and turns it into another number that is above the real axis. And we can now start to combine these transformations to get all of the modular transformations. So, for example, if I take the region that is shown in this particular picture, the gray region that is in here, it's what is called the fundamental region. And all of the other spaces that you see above the real axis can be reached by some combination of these modular transformations. So I can start with some point in this gray region in my fundamental domain, and I can move it by 1 unit to the right, and I'm now in this second region. And I can now take the negative reciprocal of that, which moves me into this small region, which is down near the axis, down near the real axis. I can now move it 1 unit to the left, and then take the negative reciprocal again, and I get into one of these even smaller regions that is even closer to the real axis. And so any of the regions that you see can be reached from my original fundamental domain by some combination of these transformations that are called the modular transformations. Well, to get back to Escher, he was fascinated by this idea of these kinds of modular transformations. And in particular, what he realized is that you can take this upper half plane and you can wrap it up into a circle. And what you get is a figure that is shown in this piece of graphic art, which is called circle limit 3, that really illustrates what is going on and all of the kinds of symmetries that are inherent in the modular transformations. Modular transformations, as I said, will be very important to the mathematics we'll be looking at after this. And so we'll be coming back to Escher's circle limit 3 very often in the succeeding lectures. Another type of transformation I want to talk about is one that is credited to August Möbius from Leipzig. He was a student of Gauss. He was actually an astronomer. And his name is generally associated with the Möbius band. If I take a strip of paper, this is colored differently on the 2 sides, and I put it together, something like this, we have a clear inside to the band, and we've got a clear outside to the band. But if I put a half twist into it, something like this, you can see that now we have a band with only one side. As we come around to the brown side, it turns into the orange side, and the orange side goes around and it turns into the brown side. There is only one side to a Möbius band. Actually, Möbius was not the first person to come up with this idea of a one-sided band. Johann Listing was the first person to do it about a decade earlier, but Möbius made it famous. Now, the group of transformations that Möbius looked at were made up of translations, rotations, dilations, and simple reciprocals. And there's a very useful way of taking a look at this particular combination of transformations. And I want to show you a short video clip now that was put together by two friends of mine at the University of Minnesota, Doug Arnold and Jonathan Rogness. So we're going to look at the Möbius transformations. These are fundamental to many, many different areas of mathematics. And as I said, the basic transformations are translation, and here we see a region that is being translated, dilations, expansions, and contractions, rotations, and then we also have this process of taking the reciprocal. And this shows what happens as we take the reciprocal, or the inverse of the points in the complex plane. We can combine the Möbius transformations, and we see here some of those combinations. This was an inversion combined with a translation. We're going to see how to combine the Möbius transformations in a slightly different way that really illustrates very nicely what's really going on using something called a projection. Rather than just working with the plane, we're going to consider a sphere that sits above that plane, and we look at a region of the sphere that is projected down onto the plane. We get our translations by moving the sphere around the plane, our dilations by moving the sphere up and down, our rotations simply by rotating the sphere. And the inversion then becomes a very simple operation on the sphere. It is simply rotating the sphere across a horizontal axis. And we can now combine these Möbius transformations just by combining motions of the sphere. So I get a rotation of the sphere about a horizontal axis, followed by a rotation of the sphere around a vertical axis, followed by moving the sphere, we get our translation, and that gives us one of the Möbius transformations. What we've seen in this video clip is actually another type of transformation that will play a very important role, and that's the idea of a projection. Taking a region or a collection of points that lies on one surface and projecting it onto another surface. That was what was done. We took a region on the sphere and we projected it onto the plane. And projections will come to play a very important role in mathematics, and they trace their ancestry right back to the understanding of perspective. A lot of the artists of the Renaissance were very interested in developing this idea of perspective, and they tended to be very mathematical. Many of the great artists of the Renaissance, people like Piero della Francesca and Leonardo da Vinci, were artists, but they were also interested in the mathematics of the art, and they saw how to combine these two. One of them that I want to talk a little bit about is Albrecht Dürer from Germany. Born in 1471, he would die in 1528. He was born in Nuremberg. He went to Italy to study. That, after all, was the place to study both art and also mathematics at this time. He went to the University of Bologna and he studied mathematics with Pacioli. He came back to Germany and he actually wrote the first book of mathematics in German. He wrote actually a number of books on mathematics, one of which was on compass and straightedge constructions. And I want to show you one of the pictures that Albrecht Dürer created using compass and straightedge constructions. It does not look like your standard compass and straightedge construction. This is his Adam and Eve, created in 1504. Obviously, there are more lines in there than just what was created with a straightedge and compass. But the importance is that the outline of the figures and the basic proportions were all worked out very geometrically. Dürer's St. Jerome, that was created in 1514, is an excellent example of the use of perspective. There are very clear lines of perspective. And one of the interesting things that comes through this perspective is that you see how shapes change. If you look at the pot that is hanging from the ceiling, the bottom of that pot certainly is a circle, but looking at it from the side, looking at it in perspective, it no longer looks like a circle, it looks like an ellipse. And that's one of the important aspects of perspective or projection, is how an object looks one way initially, and then as you project it, it changes its appearance. And this property is something that would be studied extensively in the 19th century. We know projections from a number of sources, and especially the Mercator projection, which is the way we have of representing the surface of the Earth. This was developed by Gerardus Mercator, lived 1512 to 1594. And the idea here is that you've got a spherical Earth, and we want to represent that surface on something that is flat, so we wrap a cylinder around the Earth, and we take a vertical line that runs through the Earth, a line that runs from the North Pole to the South Pole, and we simply project out from that line through the surface to the Earth onto our cylinder. And that is the standard representation of the Earth that you see in most maps, known as the Mercator projection. And it is a projection from the surface of a sphere onto this cylinder. And once we've got the surface of the Earth represented on the cylinder, we can simply slice the cylinder and unroll it in order to get a rectangular map. Someone who did important work on projections was Jean-Victor Poncelet. He was born in 1788, died in 1867. He was a student of Monge, one of the great geometers of the 18th century. Monge was somebody who joined Lagrange at the École Polytechnique, teaching at that illustrious school. Poncelet did go to the École Polytechnique and learned from Monge there. And Poncelet was particularly interested in the properties that are left unchanged when you do a projection. So as we saw in perspective, a circle becomes an ellipse, but you can't find a perspective that changes a circle into a square. What kinds of figures can you get under what kinds of projections? This is the problem that Poncelet studied. And as he studied this, he realized that there was a basic duality between points and lines. If I've got 2 points in the plane, there is a unique line that goes through them. If I've got 2 lines in the plane, they are going to cross at a unique point. Well, almost. The 2 lines in the plane might be parallel lines. But Poncelet decided that he wanted these parallel lines to meet, and so the natural place for them to meet is out at infinity. And so you get what is known as the projective plane, where you include this point at infinity as one of the possible points, so that every pair of lines gives you a point, every pair of points gives you a line. The basic idea behind the projective plane is to take all of the lines that radiate from the origin in 3-dimensional space and replace each one of those lines by a single point. Now, it becomes very difficult to actually work this out, because in order to do this, to see the resulting surface that you get, you actually need to think in 4-dimensional space. But geometers have been very ingenious in trying to visualize what the projective plane looks like. And I want to close this particular lecture by looking at one of those representations. Again, the projective plane really can only be seen in four-dimensional space. But the Boy surface, named for Werner Boy, who came up with this representation in 1901, is one of those who found a way of showing it. It really exists in four dimensions, but we get some idea of the complexity of this projective plane. In the next lecture, we're going to look at Gauss and his contributions to the development of geometry.